The scanning electron microscope. Scanning electron microscopy is one of the most fascinating examination methods. This video shows how it works in practice. Main components of the microscope are column for electron beam generation, specimen chamber, vacuum pump, monitor, and control panels. The material tester turns on the vacuum pump control and vents the specimen chamber. After pressure equalization, she can open the cover plate of the specimen chamber. Together with the cover plate, the stage pans forward. Now different specimens can easily be placed on the round stage. The filament of an old used light bulb, part of a welded tube on a sample holder, a small cobalt plate, and a golden piece of jewelry. All specimens are assembled and we are ready to start. The material tester carefully closes the cover plate and switches on the two-stage high vacuum pump as well as the electronic control. It takes about 3 minutes to obtain a sufficient vacuum in the specimen chamber and column. Meanwhile, she turns on the monitor, initializes the motorized stage and boots the microscope control. Only now she is allowed to switch on the high voltage and the thermionic cathode. For the first time, a reasonable image appears on the monitor. It shows part of the specimen stage. Using the trackball, she moves the stage within the microscope. She looks for the place where the first sample is positioned, the used filament. The magnification is gradually increased, the position readjusted, and the magnification increased again. Now a plastic and high contrast image of the filament can be seen on the monitor. Originally, the coiled coil filament was quite smooth on the surface. Caused by the everyday use of the filament, new crystals have been formed. Tungsten atoms have evaporated and the outer regions of the filament have become polygonal. But how is this plastic image generated, and how does the microscope actually function internally? The animation first shows the schematic structure from the outside. The upper part is the so-called column. It is used to generate an electron beam. The lower part consists of the specimen chamber with cover plate. In the longitudinal section, the flange leading to the high vacuum pump is visible at the bottom. Thereby, high vacuum is generated inside the whole microscope. The round specimen stage may not only be moved to the left and to the right, but likewise in all other directions. It may also be tilted and rotated. All samples to be investigated are placed on the specimen stage. To create an electron beam, a V-shaped thin tungsten wire is used, the so-called thermionic cathode. Heated up by electric current, it emits electrons into the vacuum, indicated by small dots. Below the cathode, a metallic disc with a central borehole is installed, the anode. The anode is connected with a positive pole of a high-voltage source, the thermionic cathode with a negative pole. Further necessary components have been omitted for the sake of simplicity. The strong electric field between cathode and anode accelerates the electrons downwards. These electrons are called primary electrons. They form a broad, diverging beam which hits the specimens and the stage. But this way, the beam of primary electrons is not useful yet. An electromagnetic lens focuses it finely on the specimen surface. At the point of incidence, primary electrons knock out electrons of the sample material. These knocked out electrons are called secondary electrons. Additional components are necessary: electromagnetic deflection, raster scan generator, secondary electron detector, abbreviated as SE detector, and computer with monitor. The basic principle of the scanning electron microscope is to detect the secondary electrons and use them to build up an image. To increase the number of detected electrons, a positively biased grid is placed in front of the detector. The grid attracts the secondary electrons and leads them to the SE detector. And this is the way to generate a magnified image of the sample. The raster scan generator directs the electron beam to the left rear part of the sample and stops there for a short time. The number of secondary electrons is recorded in the SE detector. The signal is amplified and displayed as a dot at the top left-hand corner of the monitor. The electron beam pans slightly to the right, stops again. The measurement is repeated. In the same way, the next points on the sample are dealt with. The principle is, many recorded secondary electrons lead to a bright image point, few electrons lead to a grey image point, and none at all to a black one. An entire row is covered in this way. Then a second row, until finally a rectangular area has been scanned and an image appears on the monitor. If not only a few but many image points are used in the raster scan, a natural-looking image of the specimen surface can be seen on the monitor. Back in reality, the material tester selects low magnification again and looks for the second sample. It is an austenitic stainless steel tube with a longitudinal weld. Invisible to the naked eye, the scanning electron microscope reveals fantastic crystals. They have grown near the surface during solidification of the weld deposit. In some crystal directions, the solidification rate is particularly high and so-called dendrites form. Dendrites are crystals with many branches and tree-like shape. On the surface of the weld, they could grow almost freely without much disturbance and can now be observed well. Last in line is the golden piece of jewelry with a gemstone. The material tester is especially interested in the chemical composition of the gold material. Does the promised gold content really exist? Which other elements have been added? She chooses a place near the edge of the piece and selects a suitable magnification. Now she makes use of a fantastic method, the non-destructive chemical analysis with the scanning electron microscope. And it works like this. When the fast electrons of the electron beam, the primary electrons, reach the surface, they knock out electrons of the specimen material. These are the secondary electrons used for image formation. What happens in detail shows a schematically drawn atom from near the surface. Just like any other atom, it consists of a positively charged nucleus and negatively charged electrons. The electrons stay in energetically well-defined shells around the nucleus. A primary electron comes from above and accidentally knocks out an electron from the K shell of the sample atom. A vacant place remains as indicated by the yellow circle. This state is unstable. An electron from the L shell fills the gap and the energy difference is released in the form of a characteristic X-ray photon. This X-ray photon is called characteristic because its energy is quite characteristic or typical for the particular element. Now another transition follows. And finally the atom repairs itself with an electron from the vicinity, a free electron. So X-ray radiation is generated during the operation of the scanning electron microscope, namely X-radiation, which is characteristic for the chemical elements present in the sample. If the energy and the intensity of the radiation are measured with an X-ray detector, then the chemical composition of the sample can be determined. Here the typical X-ray spectrum of the piece of jewelry builds up. Chemical analysis is then carried out using sophisticated methods with the help of a computer. Certain limitations must indeed be minded, but it's definitely a fine method, and above all, it is completely non-destructive, and even very small spots on a sample can be analyzed. And what has happened to the small cobalt plate, which was one of the samples? It was used to calibrate the measurement. This means to adjust it finely. The chemical analysis is finished now. Our piece of jewelry is genuine. The gold content amounts to about 70%. The balance is silver and copper.